Good evening, Hack in Paris. My name is AJIN Abraham, and I'll be talking about injecting security into web applications at runtime. So, a bit about myself. I'm an independent security consultant. I do a lot of freelance and currently doing security engineering for Aminio. I do a lot of research on runtime application self-protection by instrumentation. Authored couple of security tools like Mobile Security Framework, OWASP, Synaptics, etc. And I do teach application security at obsecx.com. So the agenda of today's talk. I'll be talking about runtime application self-protection. So the talk is about how a RAS product. I'm pretty much sure that some of you might know about the term. For some of you, it's pretty new. It's a new term coined by Gartner to categorize a new set or a new kind of security product that's out there. So the agenda of the talk is like I'll be going through the technical aspects of how an instrument and RAS work. I'll also share my research outcomes on implementing one such RASP that actually injects security into a very vulnerable Python application written in Tornado. And it's not anything about WAF or any old thing in a new bottle. So it's a pretty new stuff that I'm going to talk about. Uh, Before going into all this, let's see how is the AppSec industry now, some of the AppSec challenges that we face now. We all know that writing secure code is not really easy. I mean, myself being a security engineer, often at times I write a lot of insecure code. It's not easy to write secure code. Doing mistakes is common, and that's what people normally do. And that's the reason why all those security bugs are out there. Currently, most of them follows agile development strategies. So that means you have frequent releases and frequent builds coming one after another, maybe weekly or daily or so. So it's the chance for a vulnerability to get in is very high. I mean, a new vulnerability can be introduced, or the one that was fixed previously can be reintroduced. Then there are other problems in AppSec like session hijacking, credential stuffing, which is the headache of this century. So these are not really vulnerabilities, like session hijacking and credential stuffing are not really vulnerabilities. They are more of a design problem. So um, it's difficult to tackle with this. Most security products you have or the solutions that offer protection to you is not really enough to protect against these new threats. So we'll be talking a bit about that as well. Okay, let's talk about web framework of the web applications in a common currently. So we don't actually write web application from scratch. Like we don't write web application from PHP or Java or Python from scratch as of now. We have a lot of frameworks to ease our work. So we tend to use frameworks like Django, Ruby on Rails, Spring, etc. So these days, most of the web applications are built on top of some frameworks. And most of these frameworks offer some level of security to some level of security inbuilt with the framework. So for example, you have automatic CSRF tokens. Most of the frameworks have this feature within which it will automatically inject anti-CSRF tokens so that you don't have to worry about CSRF issues. You have templates that will escape the user input, and basically that means ideally there should not be any excesses. And you have high-level ORMs like active records in Ruby, etc., that exposes you a particular API rather than writing raw SQL query. So, which again means there is no SQLi. And at the end of the day, you need to use this secure API to make sure that your code or application is built securely. So often, many times, security issues or bugs happen when people write unsecure code or misconfigure this. So even though we have all this, some of the basic security mechanisms offered by framework, it's not still enough. So when you talk about anti-CSRF token, so myself, I do a lot of code review, and I've seen this very often. People may be like testing or doing in something in their testing environment, and they often turn off CSRF, which I have seen a lot for some APIs, etc. They have turned off intentionally or unintentionally. Then the template escaping. So the most of the templates out there, the problem with them is that they do HTML escaping, but XSS is not that simple as that. You have this concept of different context, and you need to specifically escape for each context, which is not something most of the templating engine do by default. So if you do HTML escaping in a different context, it can still result in XSS. Let me show you one simple example. So here I have a JS fiddle, and So you can see that in the bottom there is a HTML escaping function, which is something made to stimulate the typical HTML escaper. So in real world, this is how your templates escape all the user input in HTML escaping mode. So you can see on the left side the characters, the harmful characters which will get escaped into the characters on the right side. So here we have a symbol paragraph field as well as an anger tag. And we have two inputs. The first one is a typical script alert script, and then the second one is JavaScript alert. If you see here, we actually pass this user input to the escape function and then write it to these two attributes, that's a paragraph tag as well as the anger href tag. So for the first one, it works perfectly fine. You do HTML escaping and it just come back as harmless data. But in the second case, your HTML escaping is not going to help you. It just executes as a script because there is nothing to do HTML escaping on this context. And this is a different context. And doing HTML escaping on that context will never save you from excesses. So these are some of the problems. Okay. So again, when it comes to SQL injection, you have the ORMs. The problem with ORMs is that even with some of the ORMs, SQL injection is still possible. For example, in case of active records used by Rails, you can see a lot of possible way to exploit SQL injection. So there's been a wiki which has information about that. Even using these high-level APIs, SQL injection is still possible. So let's move on. And there are other application security specific threats like OS command execution, remote code injection, then server-side template injection, session hijacking, verb tampering, and the list goes on. I mean, the framework doesn't have any means to, because that's not the purpose of frameworks. Giving a basic set of security is always good, but it's not something that's designed to give you end-to-end security coverage. So most of the people, okay, we have this unforeseen threats that's going to happen. So people always think that let's use a WAF to, defend against these attacks that can happen against my web application. But the question is, can WAFs really solve the problem? The first WAF was actually here from like 1999. It was called AppShield. It's almost like 18 years of existence. And I have a question to the audience. How many of you use a WAF in your company or organization? Only one? Other people don't trust WAF as well? Okay, couple of folks. So how many of you run it in defending mode? So there are like two modes. One, you can run it on defending mode to prevent all the attacks, or one is the monitoring mode where you will actually see what is happening. How many of you run it in defending mode? None? Oh, that's crazy. I mean, you pay a lot of money and then you bought a product and you put it in monitoring mode to see what is actually happening at your organization and you don't want to prevent anything? Yeah, so the fact is that WAFs, I mean, most of them have this problem of false positives, and it's actually due to the basic fundamental idea of a WAF. Like, they use a set of blacklists to make sure that an attack doesn't happen. So the problem with blacklist is that it can actually give you a lot of false positives, plus it can be bypassed easily. So being application security guys, we know that blacklist is not the way to go on. I mean, today or tomorrow it will get bypassed. So I remember this incident. Like, we have this famous Apache struts issue came in like a couple of months back, and all the WAF vendors just suddenly tried to come up with rules to prevent that. And then they come up with a rule. It was bypassed on the second day. They come up with another rule, and then there was a new variant of the vulnerability published. Again, they have to go with a lot of other things. So in terms, if you see a typical organization, you don't really have time to, fix the code, then do all the testing, and then put it back to the production. So that's the reason most people use a WAF. I mean, you can easily deploy it and make sure that that issue won't happen. So you don't have to worry about a hotfix or so. But in reality, it's giving a little bit more pain. Like today or tomorrow, it's getting bypassed. You have to rely on new roles, etc. So that's a problem that we need to solve. So there is something that we need to understand first, like how a typical WAF works. So a WAF is completely out of application context. It works based on the request that it is coming to the WAF. So you have a basic HTTP request, it goes to your WAF, which acts as a proxy, and then based on its signature or blacklist, it will make a decision whether to allow this traffic or not. And depending upon the traffic is allowed to pass. So the basic idea is it detects an attack, not a vulnerability. Simple as that. And as I mentioned, the strengths are like blacklist, they detect attack, not vulnerability. They have no application context. So a WAF typically does not have any idea of what is happening inside your application. So the only thing it does is it actually sits as a proxy between the request coming from the client and the one that goes to the app server. Moving on, like WAF even used to downgrade your security. So you know about perfect forward secrecy, right? So like last year, Heartbleed bug was there. So which means an attacker can actually steal the server's private key from memory. And if he has encrypted HTTPS traffic, which is collected previously, he can use that key to decrypt the traffic. So perfect forward secrecy is a solution for that. I mean, if you use PFS, even if you have a previously encrypted communication and even if your private key is leaked, an attacker cannot decrypt decrypt the traffic using the key. So this is something which is really needed and really recommended. So before putting products that actually gives you a sense of security, it's better or it's ideal to have some real secure implementation before. So PFS was something that provides this level of security. Even if Heartbleed bug was, even if Heartbleed bug affects you, if PFS was there, you have to worry, but still you don't have to worry about the previously captured traffic. So the WAF can support it basically because you know you cannot use that private key to decrypt your traffic. So for WAFs to work, it has to decrypt the traffic and then inspect it to make sure that there is no issues. But when PFS is there, WAFs cannot do it. And some of them, for some time, some of them usually skip those HTTPS transactions which is using a elliptical crypto or anything that is PFS. And the other thing is, they will actually ask you to stop using PFS, use something, use a different set of specification for HTTPS, which is not really something good. And recently, some of them have come up with this concept of reverse proxy to forward the traffic again back to RASP after downloading the SSL, downgrading the SSL, etc. A couple of things like that. But that has its own performance impact. So again, TLS 1.3 is coming, and if you see the elliptical curve specification, there are a couple of them to support PFS, and it's going to be a hard time for WAF for most of them. Okay, so let's take the evolution as this. So we have WAF, which do attack detection, and prevention. And then you have the SAST and DAST tools, your static and dynamic analyzer, which do vulnerability detection. Then the new breed, which is more related to RASP, called the IAST, which gives you precise vulnerability detection, works more or less similar to a RASP. And then you have the RASP, attack detection, prevention, neutralization, etc. So these two are more like a AppSec tool, which is to be used inside the AppSec by security professionals. And these are more like a firewall kind of thing or a protection kind of endpoints, which you use just before just before your corporate assets. So moving on, let's talk a little bit about runtime application self-defense. It should be able to detect both attack and vulnerability. This is some of the characteristics that a typical RASP have. So right now, the term RASP is very generic. People have often come up with a different definition for that. So I've collected some of them and come up with a conclusion. So these are some of the things that at least you should be having. So it's not something that this is the definition, but since it's a pretty new concept. So it should be having zero-code modification and easy integration. So this is one important point of a RASP. A RASP product should not ask you to modify your code to add security to it. And then there is no need of any extra hardware. It should be able to apply the defense inside the application, not around the application or outside it, like what a WAF does. And then it should have code level insights, like it should be able to tell you like this particular line of code has an issue and the attack payload tried to reach here and this is the place where the issue is, you need to fix it here. And then, yeah, obviously inject security at runtime and there is no use of blacklist. So moving on, like I said, this is the ideal place for putting your security product. It should be inside the application, not around your application or outside your application. Okay, so again, there is some classification of RASP. So this is also not strictly defined anywhere. just I got it from a couple of researchers or couple of open source implementation that I have seen outside. There is a pattern matching there is one type with pattern matching and blacklist. So that's just your typical WAF. It's an all thing you all wine in a new bottle. It's not the right thing. That's not even it doesn't even deserve to be called as a RASP. It's just your WAF, more like a software WAF. Then you have dynamic tending, which is a good methodology, but I haven't really seen it being used in a lot of them, maybe because of the performance impact that will add up. Then there is the one by virtualization and compartmentalization. It's a bit less precise, and it's very specific to certain certain languages or certain frameworks. Currently, the one that I've seen is for JVM. And then there is the one that I'm going to talk about today. That's the one using code instrumentation and dynamic whitelist. It's specific to framework. So for a particular product like RASP to work, you need to have framework to be used in your organization. So if you write PHP or Java or Ruby or Python code from scratch, it's pretty much not that useful. But if you have application built on top of frameworks, this kind of RASP makes a lot of sense. So these are the focus of my research. I'll be talking about RASP by API instrumentation and dynamic whitelist. I'll also show you a pretty vulnerable Python application developed in Tornado and a proof of concept RASP module implemented to inject security into it. You will see a couple of code injection vulnerabilities being prevented, like SQLI, RCE, access, etc. And some of the other AppSec challenges like verb tampering, header injection, file upload protection, pass traversal, etc. And I also just give you a glimpse on my ongoing research as well. So before going into instrument and RASP, these are the couple of things that you need to understand, really. So first thing is monkey patching, and the second one is lexical analysis, and the third thing is context determination. We will go through each of these concepts. Most of the things may be aware of, you might be aware of most of the things. So monkey patching or runtime hooking and patching is a methodology that allows you to change the definition of a function at runtime. Just let me show an example. That's the easiest way to demonstrate this. So you have here, okay, you have an HTML anchor tag, and you can see that there's an on-click event handler, JavaScript, which on-click will alert, we love you. And there is a text for that, that's monkey patch. Let's click on that. But it's actually showing we don't love you anymore. So that's a simple example of monkey patching. So what we actually did is we modify we modify hook into the alert function, and we modify what it is supposed to do. We actually replace the arguments with something like this, we don't love you anymore. That's a basic concept. So that's pretty clear. Moving on, lexical analysis and token generation. So we have to use a lexer. So I'll tell you like why we are actually using all this in a couple of slides after, but before that, let's understand this first. So a typical lexer, how it works is like you give a statement to it, like something like if x greater than 3.1, it will go to the lexical analyzer, which will create a set of tokens, like if is a keyword, opening is a bracket, then x is an identifier, and greater than is an operator, and number 3.1 is a number. So that's how a typical lexical analysis works. It generates tokens. And the generic lexical analyzer, what it does is it will skip all the white spaces and comments. And also if it sees a statement which is not in its grammar, it will actually break. So I have actually modified these two things slightly a different bit to support this particular concept. So the lexer that I have will accept white space and comments. Also, it will try to categorize those things that it cannot identify. And it won't generate an error when it doesn't see an invalid token. So this is how a simple statement, int value equal to 100, and a command value is 100. So if you give it a typical lexer, it will exit like this. Int is a keyword, value is identifier, equal to is operator, 100 is constant, and semicolon is symbol. The same thing if you give it to the custom lexer that we'll be using, it also considers white spaces as well as comments. That's the only difference. So moving on, there is another thing called context determination. So this is pretty important for cross-site scripting. We'll come into that. But before that, you have a set of HTML code. You parse it using an HTML parser. And what happens is the parser will generate a DOM tree, which clearly mentions what is what. Like there's an ID tag called ident, whose value is ident. and then there is h1 inside that, the text is hello, etc. So that's a parse tree. That's for context determination. So right, we now know that what context is ID is in, what context IDEN is in, what context hello is in, etc. Okay, so you know about, we know that there have been like injection vulnerabilities from the beginning of web. There is like XSS, SQLite, and a lot more. And it is still there even today. And we were not really successful in preventing that unless we write secure code, right? So the thing that we have to understand is the reason for all this injection vulnerability is that your interpreter does not distinguish between code and data. So whatever you give it to it, it actually executes irrespective of any other instruction. So it cannot distinguish between your code and data. So if you can solve that problem, tell your interpreter that this is code and this is data, then you can pretty much solve this problem, all the injection problems. So that's what we are going to do here. So let's take a look into how we are preventing SQL injection first. This is a simple SQL query, select star from user input. So where user input is something that comes from the user, so a simple SQL query. So as per the terminologies that we learned before, we hook into cursor.execute. So before that, I'll be showing a sample Python application in which the Rust technology is implemented. So everything that I talk from a core perspective will be corresponding to Python. So cursor.execute is an API in Python that allows you to execute SQL queries. What we do is we hook into cursor.execute, and we use monkey patching to extract the statements, that is select star from logs. We do a lexical analysis of this. So select star from logs will come down as select is a keyword, and then there's a white space, so on and so forth. So you get a structure, you get a token. So for that particular line of code in the application, we have a context which tells you exactly this is a structure. And the next time an attacker try to inject something like this, which this will actually changes everything when you do an lexical analysis, and we can precisely detect it and block it. So it's quite precise. So for example, for the particular context that executes select star from user input, we learned that the token for that particular context is keyword white space, operator white space, keyword white space string. So it should ideally allow anything like select star from logs, select star from history, or select star from any other string. But the moment you try to add a code there, like select star from logs and SQL and query, which is like a code, the structure completely changes, and you can precisely detect it as a SQL injection. So let's see a demo. So here I have a vulnerable Tornado application. Let me just run it. It has a couple of SQL injections like here. Let's do the classic SQL injection payload. You can see that login success alert me. So the underlying vulnerable code is something like this one. Select star from users, where the username is coming from user input and password is also coming from user input. Pretty straightforward. Now let's see how it works with Rust module incorporated. So this is a protected version of the same vulnerable application. And for your reference, I'll just show you. The only change that I made with this application is that okay, so this is the vulnerable application on the left side, and this is this is a vulnerable application on the right side, and then the protected application on the left side. So the only change is there is something a statement called import Rust. That's the only difference there. So I haven't changed any code. You can just go down and see the same set of vulnerable code. There is nothing added there. Okay, so let's take the protected application. And for the first time, it has to learn your application. So that's the time when it actually tokenize and create the legitimate token for the particular context. So let me try something like, it says login failed. I give something like this. Okay, login is successful. Now let's try to exploit this using an SQL injection. Let's try to execute the query, and it blocked me. So what essentially happened is the structure of the tokenized structure of the query changes, and that's the reason why it got blocked. If you want to see how it see the rule for the particular context, I can just show you. So in real world, it won't be using any database or something like this, because that's again hard up another headaches and all those things. So just for the demonstration purpose, I'll be showing in a database. So this is the rule for the particular context. So you can see that this is a rule generated for the particular context of a skill. Select star from username, where something is user and something is password. So that's that. And anything that's not in the context will be blocked. Similarly, we have remote command injection. So let's consider a command like ping minus C3 user input. We hook into the command execution API. That's something like os.system or process.popen or anything similar. And then we extract the commands. That's the arguments to the function. And then we do a tokenization. We do so it all depends upon how you designed your lexer as well. So this lexer is a little bit intelligent. It can actually identify the localhost IP as an IP or domain. So even if you give a domain there, it will still classify it as a IP or domain. A bit more intelligent. And the moment you give a different command which alter the structure, it will block. So for the context ping minus 3 C3 user input, it will allow you to have ping minus C3 127.0.0.1 or Google or any other thing. At the moment you try to inject a alternate command, it will block you. Let's see a demo of that as well. So here I have the vulnerable application. There's an option to ping to a particular server. So let's do that. Pinging fine. Let's try to execute some command. And you can see that it works. Let's try the same thing in the protected version of the application. So the first time you do a legitimate request, that will learn the structure of the token. And the next time you try to give a command like this, it should block. That works. All right, so moving on, cross-site scripting. So cross-site scripting is a slightly different thing. If you try to do lexical analysis on a pretty large document, it's gonna take a lot of time, and that will actually have performance impact in your application. So we really don't want to do the same approach there. So for cross-site scripting, we will actually use this concept that we learned before called context determination. What we do is we take a set of HTML and we try to identify the places where user input come in. What is the context for that? So essentially, we'll hook into the template rendering API, and we have like, let's say we hook and collect the HTML that's going to be rendered and the the inputs that comes from the user. It can be user input or it can be anything that's hardcoded in the application as well. It doesn't matter. So we pass the HTML and we get a complete set of HTML DOM tree, which really tells us like what is user input 1 is in what context, user input 2 is in what context. So it's clearly visible that user input 1 is in HTML context and the other one is on JavaScript value context. So if you give a normal input like this to user input and user input 2, it's okay, it's fine, it just do the template rendering and gives you the response. But the moment you try to give a payload like this, the first one is a payload for HTML context and the second one is for a JS value context. We don't really block the request like a WAF does. So this is one problem of WAF. Like if it sees a open bracket or closing bracket or a dash dash, it can actually trigger a false positive and block the request, which is not something you really want. But in this case, we don't really block the request. What we do is we try to do context-specific escaping, which is not there before. So let me show you a demo. The same vulnerable application, it has a search field. Let's try the vanilla XSS payload. And Okay, it works. And if you see the reflection context, you can see that there is two reflection, one in the HTML context and the other one is on the JavaScript value context. So let's try the same thing on the protected application. We have the search field. Let's try. The first time it has to learn, so let's try with something very genuine. And then let's try to give the payload. And it didn't execute, it escaped properly. If you see the context, you can see that it's properly escaped for HTML context as well as for JavaScript context. So for JavaScript context, if you even try a payload like this, it will still won't execute because we do proper escaping for JavaScript context, which is, you can see that it prevents breaking out from the data context. So moving on, uh, DOMX, it's another thing that is actually worrying us for a lot of time. I mean, we have like lots of solutions trying to prevent this, and which are not really, it's a problem even for the people to detect it as well as, I mean, nobody wants to look into a bunch of obfuscated piece of JavaScript code and trying to figure out DOM accesses. So that is something it's quite difficult. I mean, using this approach, we can easily figure out the issue as well as prevent the issue. So the work has been previously done by Cure53. They are based out of Germany. And what they've done is, this is specifically for jQuery. So I'm just showing an example. You can do it with almost any of the frameworks. Not everything, but most of the frameworks. So what they do is they have a library called DOM-Purify, and they have a library called JPurify. So the JPurify library will hook into those jQuery functions that write HTML to your DOM, and then it passes the arguments through DOM-Purify. So what DOM-Purify does is, if you throw a bunch of HTML and JavaScript to DOM-Purify, it will remove the JavaScript part of it and give you back the HTML. So they integrated it with jQuery so that, let's say if somebody used jQuery in an insecure way, it will still prevent DOM access from being exploited. So I'll just show you a demo of that as well. So here we have a couple of libraries, and DOM Purify is loaded, JPurify is loaded. You can see that we are trying to write some JavaScript and HTML to the DOM, but in the reflection context, there is only the HTML because DOM Purify has removed the barred malicious JS from the payload. Okay, so that's a simple example for DOM accesses. Moving on, we have other interesting abstract challenges like verb tampering when we deal with API. So it's pretty straightforward and simple. What we do is we hook into the API that is reasonable for request and response handling. We learn the HTTP verbs as and when they occur. We generate a whitelist, and once the learning phase is completed, anything that comes to that particular endpoint will be blocked. So I can just show you a quick and simple demo for that as well. So we know that the home page, we have accessed the home page of this protected web application a couple of times. So we know that that should be, now that should be protected. So let's try to do a web tampering attack on the home page. Let's try to make a post request. And you can see that RAS blocked web tampering attack. Pretty straightforward. Uh, Other things that we can do is you have the HTTP header splitting attacks, which were a part of a couple of legacy applications. And even in today's application, you can see this vulnerability once in a while. A typical WAF really have to actually look for all the possible encoded combination, escaped or WAF bypassing payloads. All those things it has to look into because it's all signature based. But for us, we don't really have to do it. We only have to inspect it at the final stage when it is going to get processed. We just have to look for %0 and %0D. Hook into the HTTP request API, look for characters in the headers, and then block it if present. So here's a quick demo for that as well. We have So we just give a legitimate header and it just works. It gives you the response back. Now let's try with response splitting. And it blocks injection attempt. All right, so moving on, the other thing, file upload protection. So in the previous presentation, there was some mentioning about the typical classic PHP file upload bypass, where you bypass the restriction by changing the extension of the file name to something else. Those are things that it actually happens due to insecure coding, not really a vulnerability as such, but mostly due to the insecure coding practices. We even take care of that as well. So what we do is we hook into the API responsible for writing the files to the file system. We learn the parameters. The parameters means the path of the file and the mode of the writing. Then we create a whitelist, and we block anything that's not in the list. So again, for the demo part, let's try to upload a file. Upload work fine. Let's try to upload a different kind of file as well. Works fine. And the next time, by this time it should have learned what all the files it should actually allow to upload. And now if you try to upload a different file, like a Python file, it should block. So it's all some of the things that you can actually do if you do runtime instrumentation of critical APIs of your web application. The other thing, yeah, so path traversal is another problem. So if you see the rule set of a WAF, you will be, it's like plenty of lines like this, and it has to look for possible combination of all these escaped dot slashes in the incoming request. That's what a typical WAF. This is just a snipped version of the same. It's more than like, it's a lot of the things that a typical WAF has to look for. We don't really have to do that because we do the checks only when the path normalization happens. Same way for file upload protection, what we do is hook into the file IO API responsible for reading contents, get the directory and the file name. We learn it, and the next time when it tries to normalize or escape out of the directory, we can effectively block. So we have the classic demo of, let me show the vulnerability first. So I can actually alter the file name to read the etc password file, but let's do the same thing with the protected application. And now let's try to read it, and it blocks. So that's that. Moving on. This is something that I'm currently working on, find out a possible way to prevent session hijacking, where your users' cookies are still stolen by attacker, and they later use that to get access to their account. So which is something that I'm trying to prevent. Then layer 7 DOS, so it's a new kind of DOS with a lot of botnets out there. You can see it's pretty effective out there. I mean, it's very difficult to detect DOS attacks happening at application layer. At the network layer, you have the firewalls, WAF, everything. That works fine, but when it comes to the application layer, if you're getting DOS, for example, like you have a regex docs, you have a badly coded regex in your application, and you want to prevent that from being attacked, it's quite difficult. So those are some problems that we are actually trying to solve with this instrumental technology. Then credential stuffing, a big headache. Like whenever there's a new breach happening, people will try to dump out the DB and then try the DB credentials against your application. And I mean, people reuse their passwords a lot, so that's the reason why this kind of attacks are really successful. So that's also something that we're trying to solve. This advantages that this technology can give is accurate and precise vulnerability detection and prevention. You get code level insight. I haven't shown anything in the demo, but you really can get code level insight because you know at what particular line the issue is being exploited or being protected. It's not based on heuristics, so you don't have to worry much about false positives and other things. Then there is no overhead of SSL decryption and re-encryption because the SSL will be unloaded at the application, and we do inspection after that is done. So we don't really play with SSL. Yeah, and it doesn't downgrade your security. You can actually use any of the existing security implementation with this. And there is preemptive security. Like when a 0-day occurs or something, you don't have to run for a rule for that. Like when the first time that particular route of your application was seen, we will actually whitelist that particular route, and anything that's outside of that will be prevented, which will essentially prevent most of the 0 days. And yes, as I shown before, it should have zero code change, and it should be easy to integrate, like pip install the module and then import the module. That's it. And yes, the biggest advantage is now you can run something in production mode. You can pay for it, and you can actually run something in production mode. That's the biggest advantage. Some of the characteristics that you need to look into while, you will be seeing a lot of Rust commercial products out there. It will be coming soon. So most of them are in their early betas or so. Some of them have really good products. But these are the things that you should actually look out when you're evaluating one such Rust product. So it should have minimal performance impact because you are doing a lot of runtime instrumentation. If it's written poorly, that means your application will be slow if you are a security product, which is not something that you want. And then it should not introduce any extra vulnerabilities. It should not consume the customer's PII informations. And it should not learn the bad stuff. That's also important. If you teach it the bad stuff, then it will learn the bad stuff, and then it will not prevent against any attacks. And it should be real RASP. It should not be any fancy WAF with some blacklist. That's not a RASP. And yes, that's all, folks. Thank you.
Do we have any questions? Any comment? Yes, we have a question. If the lady, I can't tell, long hair. Okay, gentlemen, sorry, my bad. Stand up and shout it out so everybody can hear it, please.
All right, so the question was like, how does a RASP know that the learning step is finished and it knows all the routes, right? Yeah. So in real world, we have like most of the organization have this functional test where you actually, whenever a new functionality is added, you run a functional test so that all the routes of the application will be gone through. So that's something that we can actually make use of. It's not like it doesn't give you complete coverage, but that's something that we can actually make use of. So you run the RAS module inside your application when you're doing a functional test. It will go through most of the routes so that the RAS know where to hook in and where to put in the security controls. That's one thing. Another thing is, again, this is with more like a, let's say you have a security team and they are doing security test on your application. By that time also RASP can actually look for learn, it can actually learn. So the idea is that whenever if you try to exploit something, in most cases you have to actually issue a legitimate request and then you try to exploit. So by giving the legitimate request, you can learn. And of course, there is no predefined settings like you should learn only the first request. You can actually keep it for, let's say, learn for a couple of time or till you find that most of the routes are covered or most of the contexts are covered. So it's up to you. And the coverage is mostly done by this way or by generally people browsing to your application. By the time people browse your application, the RASP will learn most of the context. And also, to add up to that, one thing is it should not learn the bad stuff. So the RASP module should have some predefined set of things to make sure that it doesn't learn the bad things. So it's a different thing, but again, that's something which is a needed characteristic for a RASP.
I think I saw another question up on the front. Was there another hand up there? Somebody had a hand who no longer has a hand. All right. Thank you very much. I appreciate it. Oh, do we? We do? I don't. Okay, we have a mic over there?
Yes, I do. I was wondering if you miss a function or a field in the unique test, do we have the risk that the application will block the regular browsing? For example, if I just enter some % character and validate several times because I'm testing with a tool, and the regular user comes after and try to search his name, for example, and it doesn't work, so it could downgrade the security because it's not disponible anymore.
So in reality, we are not really, if I understand what you have asked me, so it's like, in reality, we don't really classify this as good and this as bad. So the idea is that we try to learn your application by looking into the behavior of your application, like how the application, how that particular query is supposed to be executed, or which all the feeds it is supposed to get data from. So at the first time itself, we are not doing it correct, then it's very difficult for us to find out what's the legitimate purpose of the application. Let's say your users are the first guys to use it, then we can actually get a context that, so okay, this is more or less like a username, or more like a search field where there is a user input coming from the user, which is more like a string, and then we have to process it in that way. So we learn it. But for the first time itself, if it's learned in a different way, we cannot do anything.
Okay.
Good.